Hello, my name is Björn Jörges and I am a postdoc at the Center for Vision Research at York University. The perception of self-motion, that is the perception of how we travel through space, how fast, how far, and in which direction, is a multisensory process. We have, on the one hand, visual cues from optic flow, as for example here in this video, where you can see the world fly by. And then we also have information from the vestibular system that can tell us about accelerations that act upon our body, like gravity pulling downwards or when moving forwards. And finally, we have somatosensory and tactile cues, such as the pressure on on the soles of our feet, the way our muscles work to move us forward, and so on. In our day-to-day, these cues are usually in alignment, so we can integrate them nicely and usually have a good sense of, for example, how far we've traveled. But what happens when some of these senses tell us one thing and others a whole different thing? For example, in virtual reality, we might sit still physically, but move through the virtual environment visually. So what could happen in such cases? There are two likely scenarios. One, our perceptual apparatus might completely discard the non-visual cues and rely on the optic flow cues alone. In that case, our perception of self-motion should be unbiased relative to the task in the virtual environment. On the other hand, despite the huge differences between visual cues signaling self-motion and non-visual cues signaling that the body is at rest, these cues might be integrated according to their relative reliabilities, which would lead us to underestimate self-motion, for example in VR, since our body tells us that we're not moving, effectively lowering the global self-motion estimate. So how could we disentangle these two hypotheses? We could use, for example, a postural manipulation. We know from previous research that the reliability of vestibular cues is lowered when lying down. So if visual and vestibular cues are indeed integrated according to their relative reliabilities, then the global self-motion percept should be biased less in the lying posture than in the sitting posture. If, on the other hand, vestibular and somatosensory cues are rejected and self-motion is only estimated based on visual cues, then we should see no difference between a lying and a upright posture at all. So how did we go about testing this hypothesis? We immersed our participants in a virtual 3D environment you can see here on the left. We showed them targets ahead of them, as you can see here in the video, between 6 and 24 meters in steps of 2 meters. These targets then disappeared and participants started to move forward with an acceleration of 0.8 meters per second squared. That is, they experienced optic flow that was consistent with them moving forward through this hallway. Importantly, they were not moving physically at all. When they thought they had arrived at where they had previously seen the target, they pressed a button to stop the motion and start the next trial. We recorded the travel distance as dependent variable, and overall we tested 20 participants in two postures, lying supine and sitting upright. Okay, let's talk about the results. We have here the distributions of responses for the two postures pooled across all participants. Each of the translucent dots here correspond to one data point, while the horizontal lines correspond to the mean for one participant each. And the black dot is the grand mean for each posture. Up here, we have again the means per posture, along with the standard errors. As a dependent variable, we are using the gain, which is defined as the target distance, so the distance they thought they traveled, divided by the simulated distance that they actually traveled through. Values above 1 mean that our participants stopped too early, which means that they needed less optic flow to perceive they had traveled the same distance. And lower values mean they stopped too late and needed more optic flow to perceive they had traveled this distance. We can see here already in the plot that the lying posture elicited higher gains than the sitting posture. And for statistical analysis, we used linear mixed modeling and fitted a model with the posture as fixed effect and a bunch of random effects to account for the hierarchical structure of our data. And then we computed bootstrap 95% confidence intervals for the regression coefficient pertaining to the postures. We used the sitting posture as baseline, and you can see here on the right that the regression coefficient for the fixed effect posture lying is positive, and that the confidence interval did not include 0. That is, the lying posture elicited a significantly higher gain than the sitting posture. So participants needed less optic flow to perceive they had reached the target. And this is in line with our prediction that bodily cues influence the global percept less in the lying supine posture. However, as it stands, there are two possible sources for this bias. Either this bias is really down to the perception of self-motion, or the postural change messes with our perception of the target distance. So if people perceive the target as closer when lying down, they would also need to be exposed to less optic flow to still feel they had reached the target. So we performed an additional experiment to assess distance perception. We had our participants judge whether boxes in the virtual environment were bigger or smaller than a reference stick they were holding in their hands in the real world. Participants were told to picture this box as a real object and to compare the perceived physical size to the stick in their hands. We presented these boxes at 3 different distances, at 6, 12, and 18 meters, to cover a range of distances that we had also tested in the self-motion task. In the beginning, the participants were shown boxes that were much smaller or much bigger than the reference stick in their hands, as you can see here in the beginning of the video. These boxes changed size dynamically according to a Pest staircase over the course of the experiment, such that at the end, the size converged at the value where participants thought the box on screen and the stick in their hands had the same size. This value is the point of subjective equality, or PSE, and it tells us how big our participants perceived the box to be in relation to the reference, which is, in our case, the stick they were holding in their hands. Now, as you recall, we were doing this to assess our participants' perception of distance. So how do we get from size perception to distance perception? Well, there's a thing called size-distance invariance hypothesis, which basically says that perceived size and perceived distance is highly correlated. This hypothesis is fairly well supported for most circumstances, and solidly enough so anyway for our purposes here. Here we get the results in a plot very similar to the previous one. We used the PSEs and divided them by the actual size of the target to obtain a ratio. Higher values mean that the object was perceived as larger, and with that as closer, and lower values mean that the object was perceived as smaller, that is, as further away. So first of all, we can see that the distance is underestimated for both postures, and by quite a margin, which is likely an artifact of VR presentation. We can also see that participants perceive the target to be slightly further away when they were lying supine than when they were sitting upright. And again, we found that this difference was significant. Barely significant, but significant, as judged here by the 95% confidence interval. This bias goes exactly in the opposite direction of what we would expect if the bias we find in the self-motion task was reducible to a bias in distance perception. 2 notes about this experiment. First, this result was a bit surprising, as Harris and Mander had previously found the opposite bias in a very similar or pretty similar task to ours. There are some nuanced differences that might explain this discrepancy, but yeah, we don't have the time to get into the details here. And second, there is an argument to be made that biases acting on our perception of distance might also affect our perception of self-motion, and therefore cancel out anyway. But considering this result, it seems that we are on the safe side anyway. So to sum everything up, we found that participants needed less optic flow to perceive they had traveled the same distance when lying supine versus when sitting upright. This bias cannot be reduced to a bias in perceived distance. So overall, we conclude that self-motion perception is biased by vestibular and or somatosensory cues, even in tasks that could and should even be solved based on visual cues alone. To our knowledge, we are the first ones to look at the influence of posture on perceived travel distance, but there are some studies on other aspects of self-motion. For example, no differences between an upright and a lying supine posture were found for the perception of heading direction. However, vection, that is the kind of bodily sensation of self-motion when your body is at rest, seems to be a bit more likely to occur in an upright posture than when lying supine. So overall, there's clearly more work to be done to unify these results, not only in terms of different aspects of self-motion, but also in terms of differential contributions of vestibular and somatosensory cues. We are currently collecting data on some of these questions, among others in a very exciting project with astronauts. So stay tuned and watch this space. And with that, I'm coming to the end of my presentation. I would like to thank you for your attention and acknowledge the Canadian Space Agency for their support and funding, as well as the rest of the team from York University.